In this lesson video, we're going to delve a bit deeper into the kinetic theory of matter. We're going to spend time deriving an equation and hopefully understand things a bit better along the way. To get anything from this video, you really need to make sure you've watched the one on ideal gases, because we've got some assumptions in there that we're going to be making use of. Okay, I'm not going to call them all out in this video. What we want to do is we want to get an equation that relates the pressure to what is actually going on with the particles. We know that P equals F over A. We also know that force is the rate of change of momentum. But at the particle level, pressure is made up of tiny particles, small spheres, remember, hitting the walls of the container. Let's get ourselves an expression for this. Here's a box. I'm going to make it a cube with length L to make it simple. My gas is really simple. It's only got one particle in it. And it's moving from left to right. It's traveling with a speed c, subscript x, okay, because it's going in the x direction, so cx, and it's going to hit this right side wall. Travel distance L, travel distance L again, so 2L in total. And then it hits that right side wall again. Let's say that it takes time delta t to do that. So right to left, back to right in time delta t, traveling at speed cx. So cx equals 2L over delta t, or more usefully, delta t equals 2L over cx. Right, store that away. Back to the equations. So F is the change of momentum per unit time. So F equals delta P over delta T. And the change in momentum, our momentum is mass times velocity, so it's mcx minus mcx. So obviously that's 2mcx. So F equals 2mcx over 2L over cx, which simplifies to F equals mcx squared over L. Okay, that's the average force for one particle hitting one wall. And now we need to get to the pressure. P equals F over A, so P equals mcx squared over L squared, which is then P equals mcx squared over L cubed for one particle hitting one wall. P equals mcx squared over L cubed, which is P equals mcx squared over volume, isn't it? Okay, to move on, we need a simplification. Otherwise, the maths is going to go beyond what we need in A-level physics. But unfortunately, the simplification is not totally simple because it brings in the idea of the mean square speed. We have cx squared in our equation, and we are considering traveling in a straight line from left to right and back again. That's why I have the x in the cx squared. But the particles are not all traveling at the same speed if we had more than one. So we would write that as being cx squared in these brackets, with the brackets denoting that we are now dealing with the mean. Also, some particles are traveling in the y direction, some in the z. Most are going to be at an angle. So what we do is what CIE calls a simple model . So what we do is use what CIE calls a simple model, considering one-dimensional collisions and then extending to 3 dimensions using 1 over 3 c squared equals cx squared. Okay, 1 over 3 of the mean square speed equals the mean square speed in the x direction. In other words, the actual mean square speed is given by 1/3 c squared equals cx squared. we assume that 1/3 of the particles are traveling in the x direction. Right, where were we? We had P equals mcx squared over volume, but now we know that we can change that to P equals 1 over 3 c squared over v. But we're still only considering one particle, so let's multiply by the number of particles, big N, and we have P equals 1 over 3 big N m c squared over v. That's pretty neat. We have an equation that tells us the pressure based on the number of particles, the mass, and the particle speed. We can tidy it up a bit still if we want, since Nm is the number of particles multiplied by the mass of one particle. So Nm is the total mass. Also, we are dividing by volume, so the expression contains Nm over V, which is big M over V, which is density. So we could write the formula as P equals 1 over 3 rho c squared, which is astonishingly simple. And that's an extremely useful equation when dealing with gases, since pressure and density are actually relatively simple to measure. And we already know that the speed of particles relates to temperature, so I hope you can see how powerful this can be. So let's go further. We have just proven that P equals 1 over 3 nmc squared over V, but let's rewrite it as PV equals 1 over 3 nmc squared. You might have spotted we're going to do that because we already have an equation PV equals nRT, where N is the number of moles, R is the molar gas constant, and T is the thermodynamic temperature. Equating these, we get 1 over 3 nmc squared equals nRT. Make sure you're getting the big N and the small n the right way around there. Yeah, 1 over 3 big N, number of particles, mc squared, equals small n, number of moles, RT. Rearranging it a bit, mc squared equals 3 nRT over big N. From before, Avogadro's constant Na is defined as big N over small n, meaning small n over big N is 1 over Avogadro's constant, giving us mc squared equals 3RT over Na. And if we divide both sides by 2, we get half mc squared equals 3RT over 2Na. Maybe you spotted we have an equation there that has the kinetic energy on the left-hand side, and it's governed by two constants, R and Na, and the thermodynamic temperature. One of the most significant things about this for a physicist is that we can see that c squared is proportional to temperature. You've been told this for years, that temperature relates to the movement of the particles, and now you've got the maths to show it.